Okay, welcome back to the next part, which is state space form. So you have learned the transfer function that is defined in continuous time and then in the discrete time. Now, similarly, we are going to see how you can define the discrete time, but not from transfer function, but from state space instead. So first, you need to make the model in the form of state space, continuous state space. You have practiced several times already how you can transform a transfer function into a state space form. So here the general formulation of state space. First you have state equation h dot equal to ifh plus gu, where if is constant. We can also call it transition matrix. H is state, u is control input, g is coefficient of the control input, g1 is also constant, and w is disturbance. But for many cases, especially for analysis, we consider linear system. So to simplify the analysis, usually we ignore the disturbance. Okay. And the output equation y is defined as this, where h and j are also constant. Okay. Let's see one example. The example of the ball integrator plant here. You can build block diagram for this here, 1 over s here and then 1 over s here. So from control input u, you integrate it, you get the angular velocity theta dot, and you integrate it, you can get theta. And then transform it into state space form, because this is second order. Then you have equation for h1 and h2 like this, and the output is theta. So theta is h1, so you have the constant h as 1 0 like this, so you just get h1. Okay. Actually, the state space form is not unique. It depends on how you choose the state variable. In many cases, from physical system, you choose state as some physical parameters. For example, charge of a capacitor, or voltage of a resistor, or current in inductor. So yeah, sometimes you can also transform from one form to another, and also sometimes it depends on the state that you choose. Then you can have different type of state equations. Yeah, it still have the same form. Like for example here, if you use transformation, linear transformation from state h to state psi by a invertible matrix gamma like this, and you substitute into the original equation, then you still have the form of like psi dot equal to some constant matrix times psi, and then plus some constant matrix times control input u. Okay, and also you still have disturbance, and the output equation is also have very similar form with some constant matrix times psi, and then I think I miss h, matrix h, miss h in front. Okay, so we can rewrite like here, psi dot equal to a psi plus bu, and this disturbance, and y is c times psi plus du. Well, actually, in some case, gamma is chosen to simplify the equations. Let me give one example. Oops. Oh, there's no example here. Okay. For example, if gamma is eigenvector of f, okay, the matrix of eigenvector of f, then the multiplication gamma f gamma inverse become just diagonal matrix. If you have diagonal matrix, you can easily solve the differential equation, even though you have high dimension. Okay. And let's see how we solve this kind of equation, this kind of linear equation, but you have high dimension. Yeah, we can solve it because the general solution is composed of homogeneous solution and particular solution. Okay. First, let's see homogeneous solution. Homogeneous solution is from this equation, h dot h equal to just f times hh. So this equation defines the stability of the equation itself. Okay, where the particular solution is defined in terms of the input. If you have oscillate input, then you also have oscillate output. If you have growing input, you may also have growing output. Okay. Assume that the solution of the homogeneous solution is smoothly enough that can be approximately can be defined in terms of Taylor series. Okay. So here's Taylor series where where A are vectors. Yeah, A are vectors. Okay. A0, A1, A2 are all vector, and if we differentiate this equation, then we drop the exponent of this term. For example, A0 just disappear, but then A1 you got here, and then you A2 times t minus t0 just power 1. Okay, and because you derive this h8, which means h dot, and h dot is just same as fh here, so you have fh here, right? And if you substitute t by t0, you get a1 is just f times h0, and you continue the process by take the time derivative for more order, and finally you can define h8 as this. And if you observe it clearly, actually this is just Taylor series expansion of exponential term. Okay, so you have the solution of h as exponential, also called transition matrix. Okay, then let's find particular solution. Well, suppose just assume that the particular solution is exponential of same terms, exponential term, time an arbitrary function v of t. Okay, and then the particular solution must satisfy the original equation. Okay, so just take time derivative and substitute to the original equation. You got this, and do some simplification. You just got v dot equal to this exponential term and times t and control input u. Okay, very simple term, right? And then you find the v by integrate this term. So when you integrate it, you integrate from t0 to t, then you change the variable from t to tau, right? Change from t to tau. Okay, and because hp is this matrix times v, then you got this exponential, yeah, this is matrix actually because f is matrix, time this integral, right? Therefore, the general solution is the combination of homogeneous solution and particular solution. Okay, and this one sometimes can be expressed explicitly if you know U, right? Okay, now let's see how we can transform it into discretized form. So here we can choose T as KT plus T. So it means at T0 as KT. So it's kind of from T0 to T is just one sample time step. Okay. Then substitute into in this equation, we get this form because T minus T0 is just capital T. Okay, so integral from T0 to T is just from KT to KT plus T. Okay, and yeah, actually the integration depends on the result of the integration depends on how you hold. So if you use zero order hold, you get one integration result. If you use first order hold, you get a different one. Okay. Suppose we implement zero order hold, which is most of the case. So U of tau in the period of KT to KT plus T, U of tau is just constant because we hold the value, right? So we can take U of tau or U of KT out of the integral, right? And G is also constant. We can take it out of the integral. Yeah. And then we use the change variable eta equal to the whole term in here. So d eta equal to minus d tau. And then if we substitute the tau by kt and tau by kt plus t, we got here capital T, and we got here 0. But because d tau equal to minus d eta, then you can switch the integral, become 0 to t, not t to 0. Okay? And so you have a very simplified form, right? Then we can just denote some other parameter like capital phi and capital gamma, like this. Okay, like this. Then you just have a simple form of discrete time. H at time k plus 1 equal to transition matrix times hk and plus a constant matrix times uk. And we have disturbance here. And output equation, yeah, let's say output equation, the original equation is yt equal to constant matrix h times state h. When you discretize, you still get the same form. Okay. So here just drop notation. Actually, k plus 1 here means k plus 1 times t. Okay. Now let's take the z transform. Okay, z transform of this state equation, because here you have hk plus 1. So you got z power 1 times h of z, right? And if you move this one to the left hand side, you get minus phi times h. Then you use z transform, you got phi times capital H of z. Okay, so you then you take h as a factor, because z is scalar and h is vector. When you take vector as a factor, you must have matrix here, because this phi is matrix. So here's z scalar times identity matrix I. Okay, and the right hand side is gamma times z transform of u. And for y equal to h times h of z. Therefore, the transfer function, the discrete time transfer function, is defined as a ratio of output and input to be like this. Okay? Because you move this to the right hand side, you got inverse, right? For the state h, right? For state h, you got inverse and time gamma from the right hand side. And you want to define y, because h you h from the right, so h on the left, so h on the left here. Okay, this is h. And okay, let's try one example. Yeah, from the previous example actually. Previous example of the ball integrator, you have matrix F like this, and gamma, or what I forgot, G, sorry, G. Okay, F, G, and H is 1, 0 like this. And if we can observe that if you multiply F by itself, you just get 0. Then Taylor series is very convenient, right? The transition matrix phi is a Taylor series expansion. So because f square is 0, then you have the high order term here disappear. Only have this term, and you can find it as this. Gamma again also in the Taylor series form. You only compute it for up to first order only, and then finally you just got this value. Okay, so this is a square matrix, this is just a vector, and then finally you have transfer function using the formulation here, h times this term inverse and times this term. And finally, you just get this discrete transfer function. And if you compare to this one to the example before here, it is just the same. But this one you use a Laplace transform, and then you use the table. Actually, the table is obtained from the transform that you use the sum from k take from 0 to infinity, right? Yeah, because it's single input, single output, then the transfer function of the system will be the same, even though you derive, whether you derive from Laplace transform or from state space form. But for high dimension, you don't have Laplace transform, right? You can have, but how to say? You can have what is the difference? Yeah, because polynomial function is defined for single input, single output. So as long as you have single input, single output, you can obtain transfer function same form for derive from transfer function using Laplace transform and derive from state space. But if you have high dimension, you have you can do Laplace transform, or you can do Z transform, and you can have transfer function for each state. But each state has Laplace transform as a polynomial function, right? And if you have multiple states, then you just have a set of polynomial function as a vector. So in some sense, state space form give you more information on the state, but for single input, single output analysis, you only have information of relationship between output and input, but not internal state. In our case, we have internal state, two internal states, right? So state space form give much more information and give more way to do the analysis, and also more way to design controller. You will see in the future. Okay, I think we still have 15 minutes, no, 10 minutes. We can try some simulation. So let's try in Scilab and in MATLAB. Well, so here we choose sample time capital T as 0.04 and phi, because we already define phi here and gamma here. Okay, phi gamma, H for output equation, and then define matrix A, B, C and D, and similarly you define the input U. This one you generate 0 for 200 points, all 0, but then you set the first point as 1. Okay, so here means that U3 equal to 1 0 0 like this, and all of these 200 points, 200 data point. Okay, and then you define linear system SL3 to be this system linear, and you use option here as D, which means discrete. Okay, A, B, C, D are the input matrices. Then you can simulate, you use this simulation of the system. Because the system is already state space, you don't need to transform. Yeah, before you need to transform from transfer function to state space. But here you define a state space directly. And then you define time equal to T times 1, 2, 3, 4 until 200. To be precise, you should choose T times 0 dot 0 until length of U3 and then minus 1. Then you can plot the output y3 with respect to time. The result is supposed to be like this, straight line like this. Why? Because this is the ball integrator. This is simulation of a satellite in the space. So you have a satellite float in space. Let's say it look like a cube, and so if you push, you just push it a little bit, you just push and then you stop, no more pushing. You push in this way, push this direction and then you push this direction, the same force. It's like you try to rotate it. You push like this and then it just keeps spinning because no drag, no friction, so it's spinning at a constant speed. All right. So if you look at the the angle theta, it just count up, right? Theta just count up a straight line because you have constant velocity, right? I think I have Scilab also. Yeah, actually only this last part. So I have 3 plots, so we will just look at, oh, maybe I can comment this. Comment, right click. Can I have comment? Comment selection. Okay, so I only run this last part. Save and execute. Here is the result. So you push it, it just keeps spinning all the time. Okay? So angle theta just count up.